Today we're going to be talking about mechanistic interpretability. So more specifically, we're going to start by going over what it is and why we use it. Then we're going to talk about vocabulary projection before going into targeted feature study, then going into open feature study, including sparse autoencoders, before talking about other types of autoencoders, and finally wrapping up with universality and open questions. And just a little disclaimer, a lot of the slides I reference this one survey paper about mechanistic interpretability. It's quite long, but it's very well written and very useful. So if you're looking for something more in depth, I highly encourage you to check that out. Okay, so before we talk about mechanistic interpretability, I want to just make sure we're on the same page about what we're talking about. So here I just have a little conversation between some mechanistic interpretability experts in which they define it as a subfield of interpretability, which is bottom up. So meaning that rather than in chain of thought, where we're asking the model to explain its own reasoning, a very high level approach, we're actually going into the neurons and weights themselves and trying to figure out what is actually being computed. So our main goals of the field include trying to find features which are human interpretable properties. For example, maybe some group of neurons encodes the trait reptile. Circuits, which explain how these features are extracted and interact with each other, as well as universality, which encompasses whether or not different models include the same features in circuits and can even be across different architectures. Okay, so now we're going to go briefly into why. The reason I include this slide is because mechanistic interpretability is a relatively new field, and like all new fields, it does come with a little bit of controversy where it is quite limited, and some people have called into question whether or not it's needed. However, that being said, I think even in its limited state, we've seen some really interesting progress. I just have a couple of examples on here, but you can see, like, by looking into mechanistic interpretability in protein models, they found new biological aspects of proteins. Some other examples here. So I definitely see a lot of potential in this field. Okay, now we're getting into the actual approaches in mechanistic interpretability. So the first basic starting point is vocabulary projection. So the idea of this approach is that at any point in the model, we can use the last linear layer, which is that layer which is just a linear layer on the logits, which produces them out into the vocabulary space. And we can append this at any point in the residual stream to get predictions in our vocabulary space. So, for example, let's say we have this LLM here. We're entering in the initial prompt of she is. It's going through 3 different layers, and our outputs are mother, nurse, and maid. So we have this idea that there's some sort of gendered bias happening at some point in the model, but we want to strictly figure out where this is happening. So one way we can do this is by using a vocabulary projection technique and applying a linear layer, the last linear layer, to the end of all these layers. So essentially, we're mapping this back into the vocab space, whatever the residual stream is at these points. And maybe at the first layer, we're kind of just getting some nonsense, maybe just repeating other parts. It might not even all be in the same language. However, maybe in the second layer, we're getting a little bit closer. We're getting some gendered stuff, but it's not quite related to profession yet. And maybe by this, we can make the assumption that if we're looking for neurons which encode female profession, we should start in the third layer, because the second layer, we see gendered outputs, but there aren't any professions, and the first layer just seems to be gibberish. So this is one case for vocabulary projection where we're using it as a way to figure out which layers to start your analysis on, and this is quite common in terms of projects. So you can also do this at other points. So in this example, we were only decoding at the end of each layer. Here we can do it, for example, right after mass self-attention or right after the feed-forward layer, and that is another option as well. So I do have some code that I was experimenting with this, just to kind of show how you would actually do it. So for example, here we have, we're just getting the hidden states of the model when we're running it on some prompt. You need to find a model with open hidden states that allows you to do that. Here, I believe I was using the Minstrel model. Then you can essentially just loop through the hidden states, use this model.llm head. It might be called different names in different models. This is how it's called in Minstrel. Then you are just appending this to the embedding of the last token. So this, we're gonna have some matrix of shape, batch size, sequence length, and hidden dimension. We're essentially doing this on the hidden dimension of the last token for each batch to get the predictions. Then we're using softmax, sorry. And then we're essentially just printing out the topmost predictions. I believe I also included some interesting outputs here. So this one was quite interesting. I gave the prompt "my favorite style of dance is." And you can see at the beginning, we're getting a lot of kind of gibberish output, a lot of, I don't know if that's German. This is definitely Russian. I like layer 8 not. But I actually highlighted at layer 27, there's a really clear shift where suddenly all the suggestions are types of dance. So this is really interesting. If you were analyzing this, you could say something like layer 27 in the Minstrel model clearly encodes some knowledge about different dance styles. I also have kind of a counterexample here, though, just to show that it doesn't always work out this nicely. In this example, I have "my favorite city is," and you can see, gotta scroll down a little bit more. Yeah, some interesting things. It starts saying like "definitely" in certain layers, but it starts saying Paris, layer 20 or 24, I guess, and then Amsterdam in layer 26, London in layer 28, also getting San Francisco in there, Rome. But as you can see, it's sort of spread out. You can't look at this and be like, there's one layer that's definitely encoding city information. It's clearly happening in a bunch of different layers, and this is gonna get into a problem of superposition, which we are going to talk about a little bit later. But this just kind of shows one of the limitations with this vocabulary projection technique is that you can't always find a really clean place in the model where something's happening. Yeah, and some other problems is that, okay, well, I guess first I'll mention this weight lens. So what weight lens does is it uses Logit lens on the weights themselves. And I thought this idea was really interesting. Essentially, what it's saying is that if you have like a weight matrix, the idea is that those values in the weight matrix, if you were to apply that same last linear layer to project them into vocabulary space, you could see what the weights were actually encoding. Maybe like this weight corresponds to like pancake or something like that. I experimented with it on my own. Now, granted, I didn't do all the rigorous stuff they did in the paper. For me, it didn't return anything meaningful, but I do think it's an interesting paper and an interesting idea. More interesting inspired works. So a lot of these inspired works deal with the fact, which we kind of saw when I showed the outputs, which is that a lot of these beginning layers, it's hard to tell what they're doing because they might be representing information in another dimensional space which doesn't directly correspond to the last linear layer. So, for example, this tuned lens was, I think, the initial paper that kind of explored ways to increase the accuracy of Logit lens in earlier layers. And there's been a number of other works expanding on this tuned lens idea. Yeah, there's also doing it on the gradients. So we already touched a bit on this, but the main caveats of this Logit lens vocabulary projection idea is that beginning layers might not map cleanly to the last final linear layer in terms of projecting it into the vocabulary output space. There's often not a clear turning point in terms of layer outputs, and it's considered to only measure correlation rather than causation. So it is useful as an exploratory metric or a place to start your analysis. However, because of how weakly it's proving something, it wouldn't be like a project within itself. Okay, now we are going to get into targeted feature study. So targeted feature study in general is something you do when you have a very clear idea of what you want to study. And the main case study that we're going to be looking into when we talk about this is the Indirect Object Detection in GPT-2 paper, which you may have heard about. It's quite famous in this field. So essentially, a typical step you would do in this kind of study is make a dataset of sentences with this feature present, start with Logit lens or some other method to know where to start your analysis, then perform some sort of path patching, knockout, etc., which we are going to get into. So one thing about mechanistic interpretability is, depending on the sort of subfield you're in, they use different language when talking about how to see a model. And I think it's useful to go over that a little bit just in case you want to read papers so that you won't be lost in this. But if you're reading any paper about path patching or knockout, they typically describe the model as a computational graph, where the nodes are anything with values, for example, weights, neurons, embeddings, and tension heads, and the edges are their interactions. And they use terminology like a whole graph has M nodes, and C nodes may be the nodes involved in the circuit, and you want to detect which these C nodes are by essentially knocking out the complement of M and C. So essentially what this means is we think that C nodes are involved in the circuit, and we're essentially going to try and isolate them by somehow corrupting all the other nodes. So this is sort of the basic idea of knockout. Essentially, you iteratively pick neurons in the model, you replace its activation value with a 0 or the average value. So a little side note on this, older methods tend to use 0, but if you think about it, if you're trying to study, like, for example, the effect that a neuron has in terms of predicting something like indirect object detection, if it typically fires within like a small range of like between 90 and 100, then you make it 0, you're going to get really weird output, and it doesn't necessarily correspond to whether or not that node was useful for this feature. It more just corresponds to the fact that your model is now very out of distribution, like it's getting inputs from this neuron that it's never seen before. So for that reason, most modern day approaches of this use the mean activation. So now it's still getting something normal, but it's not going to be influenced by that exact prompt. And this will allow you to see that if by replacing a neuron with its mean activation, if it's no longer able to do the behavior that you were studying, for example, like predicting the correct next word to fit with a specific grammatical concept, then you can make a claim that that neuron was somehow important in doing that. So just to kind of go more broad picture, the purpose of this is to essentially just help identify important neurons. It doesn't shed any light on how they interact. It's just showing that, oh, if we knock out like the fifth weight in layer 3, the logits for the correct prediction go down significantly. Thus, I have a hypothesis that this weight is important. Okay, so now we're going to go on to path patching. So the purpose of path patching is once you have neurons of interest identified, often through knockout or some other method, we want to test whether specific paths are carrying useful information for a specific behavior. And how we're going to do this, and if this is going over your head right now, don't worry, we're going to see a specific example in just a second. But we're essentially going to use a corrupted input and corrupted activations and compare with the real activations. So now I'm going to get more concrete. We're going to talk about the indirect object detection in GPT-2 paper. Just real quick, just to make sure we're on the same page about what this is meaning, indirect object in English is essentially a noun that follows a word like to. So if I said, I gave the book to John, John in that case would be the indirect object. And in this paper, they're specifically focused on the cases where there's two entities in a sentence, for example, Mary and John is doing something, then the thing you want to predict is Mary, just because that's the only other name in the sentence, and thus that would be the correct indirect object. So they wanted to try and find a circuit for how this was being computed, how the model knows to put Mary here. So essentially they started by performing knockout with mean activations to see which heads are important for the circuit. And like I said before, in order to do this, you need to have a data set of a bunch of sentences with the targeted feature. So for example, they might have when Mary and John went to the store, John gave a drink to, when Brian was at the park, blah, 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 Brian gave a ball to. And then essentially over all those sentences, you are iteratively knocking out neurons, i.e. replacing them with their mean activation, and then paying attention to how the logits change when you do that to try and find out which neurons are most significantly affecting that output in order to identify which are important. So in terms of path patching, in path patching you still have a data set of sentences, but instead of just having one sentence, you have one normal and one corrupted. So for example, my normal sentence might be, when Mary and John went to the store, John gave a drink to. However, my corrupted one might be something like, when John and Mary went to the store, Mary gave a drink to. And this is corrupted because now the correct answer is going to be John, because Mary is the one giving the drink. So essentially these are like slight sentences which follow the same structure, but are slightly different in terms that a different answer would be accepted as the correct answer. And the goal of this is, so the goal of this is that you have a model with a bunch of neurons in it. You run it on the clean input, which is this normal one here. Then you also run it on the corrupted input, and you store the activation of every neuron under the corrupted input. Then you rerun it on the clean input, but iteratively, you're going to be replacing the activation of neurons with their activation under the corrupted input. So for example, if we believe that neuron 7 is having a big impact on predicting the correct indirect object here, the correct name, then it should be the case that if we replace neuron 7's activation with its activation in the corrupted input, it should increase the logits for the incorrect name. It should increase the logits for Mary here, because its activation was under the sentence in which Mary was the correct answer. So this is essentially what we're doing in order to measure how much each neuron is affecting the output. And how we do this is we take the logit difference between the correct answer and incorrect answer in the normal, and we compare that to the difference when each neuron was corrupted. So here I have a little drawing, which I think is much needed. Let's say we have our normal sentence is when Mary and John went to the store, John gave a drink too. And we have, if we put in that normal input, we get the answers. Mary is predicted as 0.8 and John is predicted as 0.2. Now, let's say we give it a corrupted sentence where Genya and Dima are going to the store and Genya is giving a drink to. We're gonna run the model with this corrupted input, store all the activations for each layer, and now we're going to replace the attention outputs at this layer with their activations under this corrupted answer. And maybe here, let's say this layer in yellow is an important one. If we replace this layer with their corrupted activations, we might get the logits as Mary is still the top prediction, but now Dima is 0.4 and John is only 0.1. So if we see something like this, we can essentially identify that this layer is important in terms of predicting this indirect object. So essentially, we're going to do this for each head in each layer. And I kind of forgot to mention here that right now we're talking specifically about the indirect object attention in GPT-2 paper. This paper is focused specifically on the attention heads. So that's why I draw it like this. We're just going to be replacing the output for each attention head with their outputs under the corrupt input. Okay, so what did they find using this? So essentially they identified that these three heads significantly boost the logit difference across all the samples in their data set. Their next step were to measure what these heads were attending to try and, because now you know what is important, but you don't really know what's happening, right? This goes into like actually finding a circuit rather than just potentially important neurons. So to do this, they looked at what they were attending to, found that they were attending to the correct name. Then they used a Logit, that shouldn't be logic, Logit lens method to project the outputs of these heads into the vocab space to see right after the attention is done, if we project, are we seeing the correct name show up in the top 5 output? And if that was the case, they concluded that the head had copied it. And the results showed that these heads copied the correct names in 95% of cases. So they determined, well, not determined, but they named these heads the name mover heads and determined that they were part of this circuit. However, interestingly, they also found heads that hurt the performance. These heads attend to the correct name, just like the name mover heads. But when they did the Logit lens to project into the vocab space, instead of copying it into the output, they moved the logits in the opposite direction of the names on embedding vector. So for example, this would mean that there's, under this correct normal input here, we have Mary as 0.8. Maybe there are certain heads that take in the normal input. When Mary and John went to the store, John gave a head 2. And their specific function is to decrease the likelihood of Mary being predicted. So that was very interesting, and they hypothesized that it may be used to, like, essentially, like, loss, what do you call that word? I want to say, like, ledging, but I'm not sure if that's right, but essentially to decrease the model's confidence so that incorrect answers have a lower loss. And these are negative name mover heads. I have a little recap of the method, but I feel like I've recapped it like 20 times, so maybe that's not needed. So they also found some other heads, duplicate token heads, which identify tokens that have already appeared in the sentence. So they signal that token duplication has occurred by writing in the position of the duplicate token, so not just increasing the likelihood of that token, but specifically, like, the positional embedding is kind of being written. And then they have heads that remove the duplicate tokens. So essentially, I don't know if you've kind of gathered this from the heads that they found, but they sort of identified an algorithm where, in order to predict what the indirect object should be, you have these heads which are identifying heads that have already occurred in the sentence, then removing them from the token in the output, so you're only left with token, like, names that have only occurred once, then you're essentially predicting that name which has only occurred once. So the basic algorithm that they found is essentially, you first take all the names, Mary, John, you subtract the name that has occurred twice, that being John, then you output whatever name you're left with, which is Mary. Which is quite interesting to find an algorithm like that. So, excuse me. So this is an example of how they were able to find a circuit using mechanistic interpretability. And how do we actually evaluate these circuits? So the first metric is faithfulness, which is essentially the idea that a model, like, using just the circuit should be complete. It shouldn't be the case that there are other neurons outside the circuit which are actually heavily contributing to the desired feature. So in theory, if you're only using that circuit, you should have a very small performance gap in terms of predicting that feature. However, they should also be minimal, which essentially means that you're not including neurons which don't actually contribute to the feature that you're trying to predict. Then you also have completeness, which essentially just checks if the circuit includes all necessary parts. So if you take out some part and the behavior is still stable, remain stable under. I feel like that should be the other way around. I'm not sure, I'll check into that. But essentially, yeah, these are how you would evaluate a circuit. Okay, so that being said, so now we've talked about targeted feature study, and I'm going to talk about some limitations here, but I'm actually going to add one that I didn't find in any of the literature I read, but having done a project on this, I can definitely vouch for this being a huge limitation. But I'll get to that after I go over these. So these ones are that it's limited to predefined features, so which can be a plus in a lot of ways. If you have a specific feature you want to identify, then this is a great way to identify it. However, there might be some feature that would be hard for a human to come up with, but that the LLM is actually using. And this approach isn't going to allow you to figure out stuff like that. For that, you're going to need to use something like a sparse autoencoder. Another huge issue is polysemanticity and superposition. And this is one of the main reasons why sparse autoencoders are used. When we talk about sparse autoencoders, we're going to go more into this. There's also some causal ambiguity, it's computationally expensive, nonlinear interactions. But the main one I really want to talk about is the tokenizer. Because, as you can see here, so much of this analysis, like predicting whether or not it's predicting Mary or John or Zhenya or Dima, it all assumes that your tokenizer is using a full word. However, if your tokenizer is not using a full word, let's say you want to see if it's predicting like him or her, and you're just getting like H or something, then you don't really know what's happening. And maybe you would try and mitigate it by including H in the prompt, then trying to see whether or not it predicts IM next or ER. However, there are other issues with that. I specifically have an example with Russian where we were trying to predict case. However, different pronouns were broken up different ways in terms of case, and it was really, really difficult to move about. So I would definitely say this is more for, if you're just curious in the field, you don't really have to pay much attention to it, but if you're specifically going to work on a problem or like a research project in this field, definitely look into tokenizers of different models and think about how they're going to affect what you're actually doing, because it could really make or break your project and change a lot of the decisions you make in terms of building a data set depending on how the words are tokenized. Okay. Wait, did we already? Okay, yeah, we're here now. Okay, so I guess we're not fully done with targeted feature study. Briefly, we're going to talk about probing. The reason I want to bring this up is because it is mentioned in literature, often as like a, here's why we didn't do this sort of a thing. It's not used very much nowadays, but I think it still is useful to know about just based on its history in the field and the fact that you'll still see it mentioned in current papers. So essentially, probing is a very early method, and what it is to test whether a specific property is stored in a model's internal representations. For example, let's say in the token embeddings, we want to see if like part of speech is encoded in there somehow. Then you would take a lightweight classifier, typically just a linear classifier, which might be trained to predict a feature, like part of speech, noun versus verb, from those embeddings. With the idea being that if part of speech is encoded in the embeddings, then the classifier taking in that input should be able to learn it. So if the classifier gets good accuracy on a test set, that implies that that information was stored in whatever we were inputting, be it the embeddings or hidden states, which suggests that the model encodes this information. It does have some limitations though, mainly regarding the probe and the data you use. For example, if the task is like very easy itself, even if the model doesn't really encode very much of it into its internal representation, it might be possible that your linear classifier is just kind of learning it on its own. So this could make the probe appear more, not the probe appear more successful than it is, but make the model embeddings appear to contain more information than they do. Another main one is lack of interpretability, which essentially just means that the probe does show that there's some information present, but it doesn't explain how it came from or where the information is used, which is a big point of research in mechanistic interpretability. We typically don't want to just know what's there, we want to know how it gets there, how it's used, etc. All right, you can stretch if you want. I'm not going to hold you to it. This was mainly for an in-class lecture. Before we were talking about targeted feature study, which once again is where you have a specific feature that you're trying to measure. For example, indirect object, and you're trying to figure out how the model is computing just that feature. In open feature study, you're essentially just trying to find all the features that the model is working with at any given point. And the main model used in this is the Sparse Autoencoder, or SAE. So before I go into how SAEs work, I think it's once again useful to go into a little overview of the sort of language used in the literature surrounding sparse autoencoders. So essentially, before we were looking at models as a computational graph, here we're looking at a model as a high-dimensional graph. And it's not even really math, it's more just images, but I think it is useful for understanding sparse autoencoder papers. So just a brief review of some linear algebra. Basic vectors are the set of vectors that define the vector space of your graph. So they are linearly independent, which means that you can't create one using a linear combination of the other one. So no matter how much you add and multiply this little green line I here, you're never going to wind up on J because it's in a different dimension. So here you see the most typical graph we're working with I and J in the X and Y axes respectively, where this J is represented at starting from 0, ending at the point 0, 1, and I is ending at the point 1, 0. However, in general linear algebra, basis vectors can be anything. For example, these little E1, E2 is also a basis vector. However, for now, we're just going to visualize them as this image on the left, which is just a typical graph that we're all used to seeing. So instead of using J and I, we're going to call these basis vectors age and size. So, for example, if we're plotting features on this graph, we might put an Ottoman coin here because it's old and small. And LLMs, on the other hand, are big and new, so they might go somewhere over here. However, hot dog in the city sculpture is also new and big. So how would we differentiate between these two things? So the easiest way is to add another dimension, so essentially another basis vector, which is a linearly independent vector that can't be represented as a combination of size and age. So now we have a 3D graph, and technological is out in another dimension, ensuring that these features aren't going to get confused with each other. However, let's pretend that we couldn't add a new basis vector. Let's pretend that we're limited to a model which can only incorporate these two basis vectors. How could we represent this? So this is essentially an introduction to the issue of what superposition and polysemanticity is, which is sort of the idea that you have a need to represent more features than you have basis vectors. So in this view of the model, all of your neurons, essentially all of your weights, are basis vectors in the model. However, it can't be the case that all of your weights correspond to just one feature, because you have more features than you have these neurons or basis vectors. So you're going to have something like this, where instead of age being out on the third dimension, it's somewhere in between. It's some combination of size and technological, which can cause confusion, because here we don't really know if Sputnik's small or old or where essentially it is on the graph. So I essentially just said this, but back to LLMs, we're defining each neuron, aka weight, as being a vector in this graph. And they cannot all be linearly independent, meaning that it can't be the case that you like for example, in this example, age is not linearly independent because we can scale down technological, scale down size, add them together, and create the age vector. So if we can do that, they're not linearly independent. And this is due to polysemanticity, which is that models have more features to represent than it has neurons. So you might be wondering, like, remember how confusing it was to determine where Sputnik was on the graph? That's part of the reason is that all of these similar feature vectors were firing together and it was hard to tell them apart. So this is sort of the main idea of sparsity, which is a foundation for why sparse autoencoders were invented, which is the idea that if too many features are active simultaneously, their overlapping directions will interfere, and the model can no longer distinguish which features are present. Now, obviously, the model is able to distinguish which features are present, or else we wouldn't have like very useful and competent LLMs we see today. So we know that there must be some sparsity in terms of how the model is representing features, which is something that we are going to utilize in sparse autoencoders. We're going to take advantage of this sparsity and improve it into a structured sparsity, but I'll get more into that later. For now, I'm just kind of going to illustrate what I mean. So take a look at this graph. Do you like this graph better than the graph you just saw? And if so, why is that? So the main answer is that there's really no confusion here. For example, if we have this nitrogen molecule, it's clear that it's here because it reacts with lithium. You're not going to be, oh, well, maybe it just is kind of a prime number and speaks a bit of Turkish, so it's some linear combination of these two things. No, essentially, the model is never going to see an example in which something here is a linear combination of this axis and this axis because these axes can't really be combined. So this is sort of like the main idea of sparsity, being that these features aren't often firing at the same time. They're quite separate. So like I said before, sparse autoencoders rely on this theory of sparsity, which is the idea that there are more features that need to be represented than there are neurons. So features must be represented as non-orthogonal vectors, i.e. superposition. And in order for the model to benefit from this, these activations must be sparse. So essentially exactly what we have here. All of these vectors are not linearly independent. However, because of the sparsity, because of the fact that they're not going to be firing at the same time, it's still easy to interpret. So that is how you should sort of picture a LLM in this mindset. However, this sparsity isn't always structured or easily interpretable. So for one thing, activations of individual features might look similar. So let's say we have Korean food, something like this, exclamation mark, something like this. This in itself isn't too bad. However, it's important to note that a token would never be encoded as just Korean food, because this token has taken in the context from the previous tokens through attention. It's consumed other information through the feed-forward network. Essentially, a token might include a lot of information. So in this example, we have, I really wanted to go to Seoul Garden here in Waco, but unfortunately, after my recent experience with uncooked food, I will not be coming back. I ordered the dak galbi, and in this case, maybe this name is being encoded as some feature representing undercooked Korean food mentioned in a negative review ordered in Waco, Texas, which might look something like this. So if you're specifically looking at how Korean food is being represented, if you have a token encoding of this, it's really hard to untangle this and figure out which part's Waco, Texas, which part is Korean food, which part is negative review, etc. So before I go into how sparse autoencoders solve this problem, we're just going to go into the very basic architecture of an autoencoder. And they're a lot similar than I expected them to be. I went into this having read all the complicated linear algebra thinking, okay, this is something really mathy and really big, but essentially it's really just two linear layers is all it is. And essentially what you have is you have one linear layer as the encoder, which is taking in the hidden dimensions of the model, then putting it into some other dimensional space, which we'll get more into later. This is going to vary depending on the type of autoencoder. Then you have a decoder, which is taking in this other dimensional space, then putting it back into the original space. And essentially all you're doing is you're like putting some activation function on the encoder, then you're using the decoder on the output of this, and that's what you're returning. Then you typically have multiple types of loss. The one type of loss that all autoencoders have in common is this reconstruction loss, which is essentially just the MSE loss of the decoded versus the original. So I know that wasn't super concrete, but hopefully it will get more concrete when we start talking about actual sparse autoencoders. But before that, just a quick use case. So autoencoders are quite widely used, not just in the field of mechanistic interpretability. They can be used as a nonlinear alternative to PCA in things like classification, also used for removing noise from images and audio. Anomaly detection is a big one, and VAEs, variational autoencoders, which are for music and image generation, not state of the art anymore, but they were for a while, and I think they're interesting to learn about, so we are going to do a little tangent on that in a little while. Okay, so going back to mechanistic interpretability. So the two changes we're going to make to the basic autoencoder structure is that we're going to make the bottleneck dimension, which is that intermediate dimension between the encoder and the decoder that we mentioned earlier, we're going to make that a lot larger than the input and output space. And I want you to sit for a second and try and ask yourself why we want to do this. And in addition to that, we're also going to add a sparse loss, which penalizes the model for having too many neurons activated at once. So, and here's just kind of proof of what I'm saying. Gemma Scope, it's really cool. They actually publish all the code for the sparse autoencoder that they used, and you can play around with it and edit it as well. And you can see that this, in their sparse autoencoder, the bottleneck dimension is like 16,000 versus the input is just 2,000. So maybe you were able to answer this for yourself, but essentially the reason is that if we have the problem, or we have more features than we have neurons to represent those features, then a logical solution would be to try and map it into a space which has more neurons, so that we can hopefully only have one or a few neurons per feature. So for example, if we're taking these activations in the hidden state, some encoding of undercooked Korean food mentioned in a negative review ordered in Waco, Texas, then we scale up to this representation with many more neurons. we might get something a lot easier to interpret. Then we would scale back down and try and train this intermediate representation to be faithful enough that it could be scaled down to the original input with a low reconstruction error. So in this, what we're hoping for, what the goal is that in this scaled up version, we would have clear, understandable features which would be consistent across inputs. So something like undercooked might correspond to this neuron in all cases where something undercooked is mentioned. Korean food might be there, Waco, Texas, etc. So we kind of already mentioned this, but the bottleneck dimension is larger because it's needed to untangle superimposed neurons. It's needed so that this neuron here always corresponds to Korean food rather than it just being some subset of a really confusing cluster, which sometimes means Korean food, sometimes means exclamation marks or something like that. Then we also are going to use this sparse loss, which I have written on here. And it's essentially just measuring essentially how many of the neurons are active and penalizing for that, because if we don't do this, then maybe instead of Waco, Texas being represented by 1 neuron, the model would decide to represent it by 20 neurons, which are still superimposed, and we wouldn't be reaping any benefits. Yeah, so just a brief little side note, just to make sure we're on the same page. This linear layer, once again, if we think of our model as having a batch size dimension, sequence length dimension, and hidden size dimension, we're doing this on each token individually. So we're doing this across the sequence length dimension, which is how all linear layers work. But I know sometimes we don't always remember that at all times. So I think it is useful to remember that, yeah, this is happening on the token level. We're doing this analysis for each token. And you can do this after attention in the feed-forward layer, the residual stream, etc. And you would essentially use it on a data set of text with certain features present. For example, maybe we have a bunch of different examples of Korean food, and by looking at all those examples and comparing them, seeing which neurons we have in common, we might be able to figure out this is the one for Korean food, because in every mention of Korean food, other neurons may differ, but this one is always the same. So essentially that's like kind of a very simplified way of how these are analyzed. Yeah, and if you haven't already seen Gemma Scope, I'd really encourage you to just fiddle around with it a little bit. I think it's a really nice way of like making these things we've talked about more concrete. So here I just have some examples from here. I think this is the one that they show on their website, but you can also play in with your own. So I went ahead and I just typed this, I typed this sentence into Gemma Scope. And for those of you who don't know, Gemma Scope is essentially a huge project done by Google to train a bunch of sparse autoencoders on their Gemma model in order to try and figure out what features it is encoding. So we have, for different tokens, we have some things like negative feedback regarding experiences at restaurants. We also have names of institutions and hospitals related to medical research. So this is another example of something that we can do in open feature study that we probably wouldn't have been able to do in targeted research study, targeted feature study, sorry. Because I don't know about you, but I wouldn't have necessarily guessed that there were hospitals features being represented in this sentence, but I guess there's probably a hospital in Seoul, which is the model knows about, which is being encoded here. There's also some like really kind of simple ones, like sentences beginning with I, references to time and events. These were someone in my class named Cal, anal term, which is actually very interesting because you can look at across their database of sentences which sentences are firing for these. I obviously, as a good researcher, went and investigated the anal term. It doesn't actually fire. It doesn't seem to be related to anal at all, in short. It mainly fires for words like gal or like some Arabic words as well. So that was interesting. So how are these things all compiled? Like, how do we know that this feature is representing time? So a lot of this is done by a team of analyzers, analyzers. Good job, Darian. A team of analyzers, either humans or LLMs. I believe this is sort of like a growing field in terms of how to do these analyses, but the sparse autoencoder is never going to tell you what it's encoding. The main point is that there is going to be a lot of very messy data that you're going to have some way of analyzing, going through, and trying to match these up to features, which is a non-obvious process, non-trivial process. And briefly, we're going to go into the activations because there also is some work on that going on in the field. So ReLU is the most simple one, which you are probably already familiar with. Jump ReLU was used in Gemma Scope, and it's used to encode sparsity. So essentially, it looks a lot like ReLU, but it sort of imposes that a model has to be firing beyond a certain signal before it can activate. So if you have like a neuron that's trying to activate with a really small amount, it's just going to go to 0. And then once it's actually firing at a significant amount, the model's like, okay, yeah, you clearly have something to say here, I'll let you contribute. There's also top K, which is where all activations other than the top K are zeroed out. And this is a cool metric to use because it inherently encourages sparsity, you can train it without sparsity loss. So in terms of like speed and technical computational resource consumption, top K is a good tool to use there. So how are we... Let's say you trained a sparse autoencoder. You're trying to write a research paper, not sure if your research is significant, and you're curious in terms of how the results of sparse autoencoders are measured in the field. So the first thing is faithfulness, which is sort of the idea of, is this feature that you're saying actually there? So for example, in my personal opinion, the anal feature does not exist. I'm sorry, but if you look into the sentences that it's firing for, it just doesn't correspond to anal at all. This can be done in terms of reconstruction loss, testing if the neuron activates in the proposed way in held out test data, as well as intervention tests where the activations of that feature is changed, much like what we saw in the path patching approach. And then there's also interpretability, which is, can humans or automated systems understand and describe what the feature means? So for example, a lot of these features, like references to time, yeah, that's very understandable. However, maybe something like this is less understandable. There's usually a trade-off between the two. Usually the more understandable you make the feature for humans, the less you're actually capturing the nuances of that feature. So that's like a very major trade-off in the current field of sparse autoencoders. Okay, quick tangent time in terms of variational autoencoders. If you remember from a little bit earlier, these are autoencoders which are used for image and music generation. So we're specifically going to be talking about them in terms of image generation. The basic idea is, I'm going to start by showing it very abstractly, then we're going to go into a little bit of code, and I'm going to link some code here if you are curious and looking into it in your own time. But you start with a large input, which goes into the encoder, which you can see here. We have some encoder which is taking in a 28 by 28 image, i.e. 680 pixels, and compressing it down into a layer of size 400. So in this case, the bottleneck dimension is smaller. And this is all the encoder is doing, then it's just then doing a ReLU activation on it in the forward function. Now this is the most interesting thing about variational autoencoders. This is how they really add some spice to the traditional autoencoder framework, which is that the encoder is then going to map into an even smaller latent dimension, but instead of mapping each feature into this dimension directly, it's going to try and learn the probability distribution for each feature there if it were to be sampled using a normal distribution. So for example, how we might look at this is, instead of trying to faithfully recreate some section of the image here, it's instead trying to recreate that this feature, this square or whatnot, is typically a value of 0, meaning a black pixel, with a variance of 0.1. And that's what all these are doing. Maybe this middle is typically white, with sometimes it's a little less white, sometimes it's rare instances it's completely black, but it's typically white with a variance of 0.3. That's what this is represented as. And you might be thinking, are we doing some crazy statistics here? How is this happening? And essentially, all that we're doing is we're defining these other linear layers, which are going to try and learn how to do this through backprop. So we have this other linear layer, which is just going down to the latent dimension. However, we're calling it mu, which is the mean. And we have another one which you are calling the log variance, which is going to be used as variance. So the idea is that no, these things aren't just directly calculating the mean, but based on how we are using them in the sample through a bunch of training instances and backpropagation, after significant rounds of training, they should be trained to approximate something that would be useful to use as the mean in terms of sampling in order to reconstruct the image. This is really how you can think about these, is that it's not really the mean of the data we've seen, it's the mean that is useful in terms of creating a sampling distribution which will faithfully recreate the final image in a way that leads to low reconstruction loss. And you can see down here that this is how they're calculated, and this is how we just use them by calling that same function up there. Okay, so now we get into the decoder. So we have this learned sampling distribution. We're going to sample from it. Maybe this is 0 with a variance of 1, it's going to turn out black. This one, 0.5 with a variance of 2 is going to turn out kind of grayish, but a little bit lightish because it has that small variance. And this sample distribution is what we're going to use to decode into the final image. So this is what's kind of like creating this variation, and this is what makes the model generative, and we're going to talk about that a little bit later, but this is like a very key feature of the variational autoencoder, is that we're sampling from a distribution. So essentially, if you're like looking at this and thinking, well, how the hell does this work for backpropagation? How can you take the derivative of a random sample? That just breaks calculus. Lucky for you, other researchers have thought of this as well. And if you're not interested in this, you can just ignore it, but essentially there's this little trick where we're not actually doing a sample. Instead, we're taking a random sample epsilon, which is independent on the parameters that we're trying to isolate in backprop. So this is just going to be a constant when we take the derivative. And then we're adding just some algorithmic combination of the log variance and the mean to this random sample. So we're kind of like acting as if we were taking a sample by incorporating this randomness, but it's not actually a sample. It's something that can be differentiated, which allows us to do backprop. And if you're curious about it, you can read this little thing here. So we're gonna have the loss we talked about before, which is the reconstruction loss of how the original image compares to the decoded image, but we're also gonna have KL divergence loss on the mean and variance to ensure that the values don't vary too much from the standard normal distribution. So I want you to pause here and try and think about why this might be needed. So essentially we're saying that we want these little mean and variance values to be close to the standard normal distribution range. Oh, and you can see here essentially how we're calculating that. So the reason we're doing this relates to generation. Essentially, when we generate, we're going to be giving it this vector of random noise, which is sampled from this distribution. So we want it to be something that the model knows how to interpret. We want to be close to the examples that it's seen, so that if we give it this random noise, it'll give us a good image from it. It'll reconstruct it into something that looks like a normal image that it's seen in its training data. So this is the clever trick that allows for generation to happen in these models. So as you can see, I did a little side project on this just to have some fun with it, see how it works. And you can see my beautiful, beautiful numbers. Some of the 9s look okay. That's like a decent 8. Some of them I wouldn't necessarily call numbers. I think that's being too generous, but if you're curious about looking at the full code, you can definitely take a look at that and see what's happening. I tried to comment it quite thoroughly to make it clear what's going on at each step. Okay, now we're back to mechanistic interpretability, almost done with the lecture. The next major question in the field is universality. So this is, do models with different training settings learn similar representations? Are the circuits in smaller models reused or improved upon in bigger ones? Is the sort of features and circuits consistent across architectures? And do they work across different languages as well? So for example, in terms of across architectures, there's an interesting paper that came out quite recently about studying mechanistic interpretability in terms of transformers and state space machines, which are kind of a newer in architecture, which show very good, similar performance to transformers, are a lot less computationally heavy in terms of inference time. However, they don't do as well for in-context learning, so things like learning things from the prompt. So they haven't been widely used, but they're still kind of on the cutting edge of research. And they actually found like a 0.74 similarity score with 30% of the features being a near exact match, which is quite interesting considering they're completely different architectures. Okay, so open problems. So we have interpretability versus optimization, that thing I talked about before in regards to sparse autoencoders. Validation bottlenecks, which is sort of, I don't know if you notice this every time I talked about validation, it's all very like conceptual, a little bit abstract. There's no like real standard framework for doing it. A lot of methods only show correlation rather than causation. There's a lot of human intensive labor, which is slow and doesn't scale, but you know, it also provides jobs and interesting work for researchers, so I don't know if that's necessarily a con, but I could see someone using it as a con to write a good research paper about doing something more LLM based. Polysemanticity and superposition across layers. So this is something I kind of alluded to in the first example with when I was decoding the cities and the minstrel model, we saw that the city computation is clearly happening in different layers. Some layers are predicting Paris, others are predicting San Francisco. If we were to look into that, we'd have to be aware that it might be the case that different neurons and different features are interacting together to create those predictions. Cross-architecture behavior prediction. So these three things at the bottom, I think are like the most interesting directions that a lot of people want to go in. Essentially, we want to be able to know what the model is going to do, and we want to be able to edit it. That's like one of the main goals of mechanistic interpretability, is to really understand what's going on in models and maybe take out features that we don't want, add in new ones, or use it to improve training. Okay, I don't have the quick quiz for you guys, so instead I'm just going to say thank you so much for making it to the end of this video. I know it was quite long, but hopefully you did learn something about mechanistic interpretability, and good luck in whatever your next step is with this information.